Okay, everybody. Good morning. Happy Tuesday. Happy back together. First off, I apologize for last Thursday. I'm really sorry that I had to cancel class last Thursday. One thing I will really stress is that is not the norm for me. I very rarely cancel class, but I had an emergency related to the beginning of fall quarter at De Anza that I had to take care of, and so it was something I couldn't get done later in the day. It was like either do it now or there was going to be hell to pay. So I really apologize for that. That's not a normal thing for me. That being said, today we're talking about what I consider to be a really cool topic, and it has to do with, in a very real sense, some pretty crazy magical stuff that happens. And so let's jump in and talk about it. So today we're talking about this thing called latent heat. And the question that I have for you, and I will put the link here in chat, is why does sweating cool our bodies down? Why does sweating cool our bodies down? So I'll put that in chat one more time. Take a few minutes, think about a good explanation. A few more people are trickling in now, so I will continue to post the link. Why does sweating cool our bodies? Oh gosh. Okay, give me 1 second. Gosh, I hate it when Google Forms does that. I am so sorry. Give it a try now. So hit refresh and give it a try now. Sometimes Google Forms does that. Thank you for letting me know. All right, awesome. Let me post the link one more time. All righty. And then give me 1 second. I'm gonna go grab something, a really cool demonstration to show you all in a few minutes. I'll be right back. So I have a really cool demonstration I'm going to show you all in a moment. Okay, let me paste that link one more time. All right, it looks like almost everybody is done. Looks like almost everybody is done. Okay, perfect. Let's see here. Okay, good. Perfect. Okay, it looks like we have just about everybody. Let me paste this link one more time. I see a few more people have trickled in. But let's take a look and see sort of what the predominant answer is. So, why does sweating cool our bodies? I used to ask the question, why do we sweat? And what I noticed was that the predominant answer was, well, it cools us. But what about sweat actually cools our bodies? Well, this really does get into what we're going to talk about today. And just to kind of go over this, and then I have a cool demonstration I'm going to show you real quickly. So let's take a look here. Sweat releases a liquid. When liquid comes into contact with air or wind, it cools our body down. So if you've ever been really wet, like if you've ever poured water on yourself and then put it up to a fan or put it up into wind, you kind of feel cold. That's definitely something that happens. It releases moisture on your skin, therefore cooling you down. Sweat is mostly water, which is really good at conducting heat away from our skin. Ooh, here we go. The action of sweat evaporating from our skin. It makes our skin feel cooler. So something about evaporation causes this. When water evaporates, it sucks heat out of its surroundings. It sucks heat out of its surroundings. This is why when you get wet and stand in the wind, you feel a lot colder than you would if it's just dry. Sweating cools our body down because when we sweat, the heat in our body comes out with the sweat. Our sweat helps us feel cooler by releasing moisture onto our skin, trapping some of the heat, and when it evaporates, it removes that heat. So I'm getting predominant answers now that are a lot about something about the water evaporating cools us down. Something about the water evaporating cools us down. Let's see here, sweating allows our body to release sweat through our pores, and then it evaporates, and as it evaporates, it cools down our body. So once again, evaporation. I'm not exactly sure why. That's totally fine. Makes us damp, and when you damp, wind feels cooler. When sweat hits the air, it evaporates, and that causes you to cool off as it's evaporating. When sweat evaporates, it cools down the body and removes the heat. Also, when you're wet, you feel cooler in general. Okay. Sweating cools our body down because the sweat evaporates the air, which makes temperature on your skin cooler. Sweating cools our body because as the sweat is leaving your body, it turns into mist, cooling your body down. Sweat cools your body by first making your skin wet, and then when it evaporates, it takes heat energy off. Sweat evaporates. Water cools faster than our body does. Not quite, but good guess. When sweat gets in contact with the air, it evaporates, and hence it makes our bodies cool. A lot of you are getting that main predominant idea. Okay, so it has a lot to do with water evaporating. Well, if you've ever wanted to impress your friends at a party, if you've ever wanted to impress your friends at a party, there's actually a way that we can use that same science to do it. So here's how. If you've ever wondered, so let's say you go to a party, and let's say you're over 21. I do not condone underage drinking. I don't really care, but legally I don't want to lose my job. I do not condone underage drinking, obviously. That being said, let's say you go to a party, and if you're under 21, let's say there's a bunch of sodas there, and they are they're room temperature, and your friends are bummed because they've got these room temperature sodas, boring party, right? Well, what if I told you that you could become the life of the party by getting those sodas cold really, really quickly? Here's how to do it. So I grabbed the closest can to me. I have a little beer can collection here. This is a stout that I'll enjoy this afternoon, right here. Let me take the temperature of it just to make sure that I'm being fair with everybody and not misleading anybody. Take the temperature of this beer using that same thermal radiation gun that I used a few weeks ago. And sorry that it keeps cutting out. The temperature of the can was 72.2 degrees Fahrenheit. All right, I have not doctored this can in any way, shape, or form. I've not done anything wrong to it. Okay, I'm gonna get this can to drinkable cold temperature within just a few minutes. Here's how. So I have right here a nice big bowl. And what I'm actually going to do is I'm going to fill this bowl with some ice taken from my freezer. Ice taken from my freezer. Probably be better if I had more ice than this, but use what you have. Ice taken from my freezer. Okay. Some ice taken from my freezer. I dropped a cube down here. We're not drinking the ice, so it's okay. So ice taken from my freezer. And then salt. All right, so this is just normal, ordinary table salt. Generously sprinkle it. Generously sprinkle it onto the ice. And then finally top it off with a little bit of normal plain ice water. Probably need some more water than that. Or sorry, normal plain temperature water. Apologies. This was normal temperature 71.6. So it was room temperature water. Then what you do, you take your can and you put it in that mixture and you give it a good stir. I actually pulled up a second camera right here. So if you actually scroll on your Zoom, you'll see the second camera right there. Take it, shake it up. Probably could use a little bit more water in the bowl, but I'm not gonna make you all wait again. I wanna be respectful of your time. So take it, shake it up, and let's give it a few minutes just to kind of sit there. While I'm doing that, let me actually reposition this camera so that, let me reposition this camera so that you can see the bowl. So the bowl is right here. I'm not doing anything to it. I'm not doctoring it in any way. It's just sitting there. And tip this down just a little bit so you can see the bowl there. Okay, so here's what's gonna happen. Let's give it 5 minutes. So it's 10:44 right now. I'm gonna come back to this at 10:49. All right. While we're doing that, or while I'm waiting for that, let me talk a little bit about how this actually relates to this class. Cooling a beer really fast, how that relates to the class. Good to give it a little stir just to kind of get it mixing in there. Well, let's talk about how this relates to our class. So today, the topic that we're talking about is what is called latent heat. It's basically a fourth heat transfer. So if you remember, I talked about conduction, convection / advection, and radiation. This is a fourth special type of heat transfer. It explains why sweating cools your body, and it also explains why really crazy stuff happens in our atmosphere. So here we go. We're going to talk about what latent heat is and how heat is exchanged with water as it changes phases. As it changes phases. And I'll tell you what the salt was all about in a few moments too. Okay, so first off, what if I told you that we're actually surrounded by water right now? Between 0 to 4% of the air that you're breathing right now has water in it. Usually never as low as 0, never as high as 4. There's always at least some water in the air. And don't believe me? Well, if you've ever had a bad hair day, like I did circa 2006, you know that it's humidity that causes bad hair days. It's humidity that causes bad hair days. On the other hand, when it's really humid outside, it can also feel really, really hot, really, really muggy, really, really miserable. If you've ever been to the East Coast of the United States in the middle of the summer, you know what I'm talking about. 90 degrees with 90% humidity, it sucks. Well, all of that to say this. Our planet is unique. Earth is unique in the solar system. And the reason why is because Earth is the only planet in the solar system where water is readily available, naturally available. It is there in all three phases. And you can even see that on this image right here, this big blue marble. All of that blue water, that is liquid water. A lot of the white, those are clouds, and embedded in those clouds are tons and tons and tons of what's called water vapor. That's water as a gas. And then down here near Antarctica, down here near Antarctica, that is ice water. That is water in a solid form. So all of that to say, Earth is the only planet where we knowingly, 100% confidently, there's some dispute about Mars, where water exists in all three phases. This is believed to be crucial for supporting life on Earth. And the three phases are solid, liquid, and gas. Solid, liquid, and gas. Well, the truth is, this water does not like to stay in one phase. As you're actually looking right now at this bowl, what's actually happening inside this bowl right now is that the ice is actually melting into liquid water. The ice is melting into liquid water. Well, water exists in all three phases, but it doesn't like to stay in any one phase. Rather, water is constantly changing phases. Even right now, as you speak, there is water that is condensing around you. My Starbucks cup has condensation on the exterior of it. I ordered an iced coffee this morning, condensation on my Starbucks cup. Even this bowl has water condensing on the sides of it. That's a phase change. Inside the bowl right now, water is melting. That's a phase change. Well, what happens is, as water undergoes a phase change, it goes from one phase, either solid, liquid, or gas, to another phase. And the ones that I'm pretty sure that you're all used to are evaporation condensation, freezing, melting. Those are the pretty common ones that we talk about. All right, let's check in with my can of beer right here. I just pulled it out. It feels actually very cold to the touch. Let's actually give it a moment just to kind of get the cold water off of it. I'll dry it off real quick. Use my shirt. Not doing anything funky to it. And now let's measure the temperature. So just notice, this was room temperature when I put it in that ice 5 minutes ago. Let's measure the temperature now. Okay. The temperature now, 56.5 degrees. 56.5 degrees. So in the 5 minutes that I had it in this ice bath, it has cooled from 72 to 56 degrees. That's a 16-degree temperature drop in just 5 minutes. Now, if you actually had like a normal thing of ice water, that cooling would take much longer. It would take more like 15 or 20 minutes. It would take quite a bit longer. So what is it about the salt that actually caused this to happen faster? And if I leave this in for a few more minutes, it's going to get even colder. Well, the reason why the salt makes a big difference is that when you put salt on ice, that causes the ice to melt at a cooler temperature. So now, rather than melting at 32 degrees, it might melt at 20 degrees. Well, in order for it to melt, it actually needs to absorb heat from its surroundings. That heat is what is called latent heat. So when water undergoes a phase change, it needs to suck heat from its surroundings. Well, the surroundings for this ice water consist primarily of this can of beer, this room temperature can of beer. So all of the heat is being sucked out of the liquid inside this can and being brought into the ice and the liquid water here as it's melting. So all that heat is being sucked out of the can, causing it to cool relatively rapidly. And if I give this a few more minutes, it's going to, like in a matter of just a few minutes, it will be like drinkable temperature cold. Usually a beverage that you would drink at out of a cooler or something would be around 45 degrees. We're almost there as it is. So if I give this a few more minutes, it will reach that temperature. But the reason why this happens is that when I put the salt on the ice, that immediately triggered melting. Well, in order for ice to make that jump from solid to liquid, it needs to absorb heat from its surroundings. And that heat is what is called latent heat. What's interesting is that the heat itself, as it's absorbed by the ice, as it's melting, it actually doesn't increase the temperature of the ice. So if I were to actually measure the temperature of this icy, briny, watery mixture, which I'm doing right now, if I were to measure this temperature, I got 9.1 degrees Fahrenheit. So already cooler than that melting point, and yet melting is happening. 29.1 degrees Fahrenheit. Well, as ice is absorbing that heat, its temperature isn't going up. Instead, what is happening is it is going towards melting the ice. It is going towards breaking down the bonds that ice has, that those water molecules have with adjacent water molecules. It's allowing them to spread out. But because this heat doesn't actually go towards warming the water itself, it is oftentimes referred to as a hidden heat because it actually doesn't affect the temperature of the water. Instead, it's solely focused on changing the water's phase, changing it from solid to liquid. Now, that being said, another cool experiment you could do at home if you wanted to is get a pot of ice water or a beaker of ice water. You can even use something small like this. Put it on a hot plate and stir it up, and every minute measure the temperature. What you'll actually notice is as long as there's ice still in the liquid, the temperature doesn't really go up. Why? Because any heat that's being absorbed from the hot plate is actually melting the ice. So all of that heat is melting the ice rather than actually going towards changing the phase. So how does this all relate to meteorology? How does this all relate to weather? Well, it relates to weather because surrounding us right now is a bunch of water vapor. And sometimes that water vapor condenses. And when that water vapor condenses, it exchanges heat with the atmosphere. Heat is a form of energy, so it provides energy to the atmosphere, and it's that energy that can actually fuel storm systems. Things like hurricanes. So right now, a tropical storm just hit land near Texas, Tropical Storm Beta. Yeah, so we've had so many this year that we actually ran out of names for them. Well, what's actually happening is that a lot of latent heat has been sucked up into that storm, fueling it, allowing it to strengthen. So let's talk about this a little bit more. Really quickly, just for kicks and giggles, let me measure the temperature of my can again. Okay. 46.8. That's usually a pretty good serving temperature for a beer like this. So this thing went from room temperature to drinking temperature in just about 10 minutes. Maybe a little bit more, like 15 minutes. It would take half an hour, 45 minutes, an hour to do this using any other method. So that's a way that you can impress your friends at home. That's a way that you can impress people at parties. If they have a bunch of room temperature sodas or room temperature beers and you need to get them cold quick, dunk them into a huge ice water bath with lots of salt in it. All right, that's enough of that. I will enjoy that tonight. Let me leave. Turn that off. Okay, let me set that down here. All right. So, bottoms up, bro. Too early in the day for it now. I only grabbed that can because it was the closest room temperature can I had. I had some soda, but it was in the fridge. Okay, so how does this all work? Well, in order for me to explain that, I have to introduce a few terms to you. The terms come from the different phases of heat. And the different phases of heat are determined by how much energy is present in the water itself. So the three phases of heat are as such. The lowest energy state is ice. So solid water, that's the lowest state. The second state, the intermediate state, is liquid. And the highest state is gas or water vapor. Okay. When water undergoes a phase change where it jumps from ice to liquid, so this is when ice melts. That is called moving up a phase. It has moved from a lower energy phase to a higher energy phase. And then when liquid evaporates, it goes from liquid to gas. That is also moving up a phase. So melting, evaporation, there's a third one called sublimation. Those are all moving up a phase. And in order for water to make that quantum leap, in order for water to make that jump from liquid to gas or from solid to liquid, it needs to absorb heat from its surroundings. It needs to absorb heat from its surroundings. So if I have a bead of water, a little water drop in the atmosphere, and it evaporates, it has to suck in heat from its surroundings. And in doing so, sucking in that heat from its surroundings, it cools those surroundings. This is why sweat cools your body. Because when that water on your body evaporates, it sucks in heat from its surroundings. It sucks in heat from its surroundings. Now, on the other hand, when water does the opposite, when it either goes from a gas to a liquid, that's called condensation, or from a liquid to ice, that's called freezing. In order for it to do that, it needs to lose heat. It needs to give heat up. And so what it'll actually do is it'll give heat up with its surroundings. It'll give heat to its surroundings. That's called moving down a phase. And when that happens, the water releases heat to its surroundings, and it warms those surroundings up. This is going to become really, really important in about a week and a half when we start talking about stability. When water condenses, it releases heat into the atmosphere. And it's that heat that fuels thunderstorms and fuels hurricanes and fuels all kinds of crazy stuff. So when water cools, when water freezes, or when water condenses, it releases heat into its surroundings. So heat is removed from the atmosphere by water as it moves up a phase. This is why sweating cools your body down. On the other hand, when water is condensing, that same heat is now released into the atmosphere. And this warms the atmosphere up. So if you've ever wondered why on a very humid day, why it just doesn't cool off, why it just doesn't feel right, it feels miserable, it feels sweaty, sticky, gross, and all of those other feelings. Well, the reason why is because when water moves down a phase, it releases heat. And so when there's a lot of water condensing, that makes it feel hotter than it actually is. Not only that, but adding to that, the sweat on your body can't evaporate. And since the sweat on your body can't evaporate, your internal air conditioner essentially breaks down. So now your body temperature goes up, it feels much more miserable, and now you're covered in sweat that can't evaporate. Ew. Sounds like a horrible day to me. Sounds like a day I would not want to write home about. So that's why humid days are so miserable, whereas why dry days don't feel so bad, because all of that moisture is evaporating, keeping you cool. Another example of this, have you ever stepped out of the shower on a cold, dry morning and felt cold? Anybody ever experienced that before? Step out of the shower, cold, dry morning. That's the worst. Well, the reason why is because as soon as you step into that drier environment, all the water that's on your body is evaporating. Same is true if you've ever gone swimming and you've stepped out of a pool and maybe you feel a little breeze and it suddenly feels chilly. Once again, it's because water is evaporating from your body, making you feel colder. Insane if you ask me. So all of this being said, I'm going to now use a few more phrases. The phrases I'm going to use are what are called cooling process and warming process. When water moves up a phase, that cools the atmosphere. We call that a cooling process. So yes, evaporation is a cooling process. Because when water evaporates, it actually takes heat away from the atmosphere, cooling the atmosphere down. The same is true when water melts. When water melts, it takes heat away from the atmosphere, cooling the atmosphere down. And in fact, it can even skip the middle person. It can even go straight from ice over to vapor. It can go straight from ice to water vapor. That's what we call sublimation. That's going to become important in a few weeks when we talk about precipitation. On the other hand, when ice moves down a phase, either it condenses into liquid water or it freezes into ice, that releases heat into the atmosphere, warming the atmosphere up. And then you can also skip the middle person in this process as well and go from water vapor straight over to ice. To go from water vapor straight over to ice. That's what's called deposition. So in essence, if I were to ask you to remember anything, there are two phrases I want you to remember. Melting and evaporation are cooling processes. Condensation and freezing are warming processes. Cool story, Terrence, but that sounds really confusing. Yes, I know. It does sound very confusing because right now I'm telling you, evaporation is a cooling process. Doesn't that kind of go against convention? When you usually think of a cooling process, you're thinking of something becoming cooler. But when you heat water up and it evaporates, aren't you heating the water up? Absolutely. Absolutely. But it's not the water that we care about. We're meteorologists. We don't care about the water. We care about the atmosphere. So what I'm talking about when I say a cooling process, I'm talking about from an atmospheric perspective. When water evaporates, it takes heat away from the atmosphere. Therefore, the atmosphere has lost heat, and therefore it is now cooler. On the other hand, when water condenses, it releases heat back into the atmosphere, warming the atmosphere back up. So from an atmospheric perspective, the atmosphere is warming up. Another way to think about it, let's say you and your little brother decide to, or let's say it's your little brother's birthday and you give him a card with $50 in it. From your perspective, you are now $50 poorer. From your brother's perspective, he's now $50 richer. Well, in this case, from the water's perspective, when water evaporates, the water's warmer. But from the atmosphere's perspective, the atmosphere is now cooler. So when I talk about cooling processes versus warming processes, What I'm actually talking about is the atmosphere. Evaporation cools the atmosphere. Condensation warms the atmosphere. Condensation warms the atmosphere. Okay. Why is this important? Why would I spend the last 40 minutes talking about it, showing a demo, showing you how to cool a beer really fast? Why would I bother talking about any of that? Well, the reason why is because this allows water to become a major source of energy for the atmosphere. So a few weeks ago, it's been a few weeks, so I haven't been able to do this corny dance recently, but when air rises in the atmosphere, it expands and it cools. As water rises in the as air rises in the atmosphere, it expands and it cools. Well, embedded in that air that's expanding and cooling is moisture. Well, at some point as the air is expanding and cooling, that moisture will eventually reach a condensation point. It will reach a point where the water begins to condense. At that point, heat is released into the air. This allows that air to continue to rise, where it then keeps expanding, keeps cooling, keeps condensing. That allows it to rise even more. And what this can actually do is this can allow clouds to become really tall. If you've ever seen a cloud that looked like a big puffy cloud, maybe with an anvil-like head on the top, something like this. We see them even here sometimes. The reason why this happens is because there's a lot of moisture in the air. And that moisture allows the air to rise really, really high. And the higher it gets, the taller the cloud becomes. The more intense the rainfall is going to be inside the cloud. You're also going to get differences in electricity that could actually cause thunder and lightning. And so it is this release of latent heat that actually allows thunderstorms to develop and even hurricanes to intensify. This even allows hurricanes to intensify. Well, why don't we get hurricanes here in California? Have you ever noticed that? We don't get hurricanes here in California. Right now, they're worried about them on the East Coast. There was Tropical Storm Beta, which just hit Texas. There is Hurricane Teddy, which is heading up towards Canada now. There's another tropical storm near Portugal called Paulette. There's been a lot of these recently. Well, in order for a hurricane to develop, it needs lots of warm, moist water, lots of warm, moist oceans. And if those oceans are at a certain temperature threshold, there's enough water evaporating that then feeds into the storm. As this evaporated water rises in the atmosphere, it condenses again, and that condensation releases heat into the storm, allowing it to intensify. Well, there's actually a magical threshold. Waters need to be at least 78 degrees or higher. If they're lower than 78 degrees, there's not enough energy for a hurricane to intensify. However, once they hit that magical threshold, the water is now energetic enough to allow hurricanes to intensify. However, once a hurricane hits land or it travels over cooler waters, it rapidly weakens because it loses that energy source. It rapidly weakens. So this has already happened with Tropical Storm Beta. Yesterday, it hit Texas, and just in the last 12 hours, it's begun to weaken. It's begun to fall apart. It's begun to fall apart. So as a hurricane intensifies, it sucks up all of this warm water from below. And then as that water rises, it releases the heat into the storm, allowing it to become more powerful. Well, case in point, this hurricane is now a little bit more ancient history, but it's still one of the most notorious hurricanes in modern history. Hurricane Katrina. So how many of you have heard of Hurricane Katrina before? See a couple of hands up. A few people have heard of Hurricane Katrina. Awesome. Thank you. So Hurricane Katrina actually formed over here. It moved its way over southern Florida and then down here into, it moved down here into the Gulf of Mexico. The Gulf of Mexico is actually home of some of the warmest waters in the world. Gulf water can sometimes top 90 degrees Fahrenheit, easily enough for a hurricane to intensify. Well, right here, this little magical area right here, if you actually take a look at the colors of these dots, and by the way, just to demonstrate, or just to clarify, Hurricane Katrina's track was like this. Hurricane Katrina's track was like this. So as it was traveling over this patch of water, it underwent a process called rapid intensification. Wind speeds went from roughly 115 miles per hour to 175 miles per hour to roughly 175 miles per hour in less than 12 hours. That is a huge jump in wind speed. That is a huge jump in intensity. And for that to happen in 12 hours is astonishing. Well, the reason why it was able to do that was as it traveled over this patch of Gulf water, it just got hungry and it just slurped all of this warm water up. And all of that water provided a lot of heat, a lot of latent heat to fuel the storm. Now, once a hurricane slurps up all of that warm water, what's left below? What's left below in the ocean? Any guesses? Let's see here. Somebody said something in chat. Sand. The water's much deeper than that. So we're just talking about that very surface layer of water being slurped up. What's below that? Cooler water. Yes. So as that warm surface water is being slurped up, what's left below is cooler water, water that doesn't get as much sunlight. Well, if you actually notice right here, whoops, sorry. If you notice right here, this little patch of water is actually much cooler than its surroundings. And the reason why was because as Hurricane Katrina tracked over this area, it slurped up so much water, so much of this warm, moist air, so much of this warm water, that it actually left a patch of cooler water behind. That process is what's called upwelling. And it's very common when a hurricane when a hurricane is in an ideal environment to intensify, it can happen like that. You can go from a weak hurricane to a killer strong hurricane in a matter of just a few hours. And this has happened recently. Hurricane Teddy just last week did this. It went from a pretty weak tropical storm to a major hurricane in just a few hours. Hurricane Wilma in 2005 did this. Dorian last year did this. So this is actually very common for hurricanes to do this. But But it's all because that warm water contains a lot of latent heat. And as that water condenses into the storm, it releases that heat, powering the storm. And these storms get really powerful. Would be cool if it just freezes the water. Whoops, sorry, let me go back real quick. Yeah, it would be. I think that'd be kind of cool if it did. Almost like that day after tomorrow hurricane, the one that like freezes you on contact. Doesn't quite work that way, but it would be kind of cool if it did. So that being said, as soon as the hurricane hits land, it rapidly weakens because it loses that energy source. This is why you don't see hurricanes over land. This is also why you don't see hurricanes here. If you've ever been to our beach, so can storms last forever if the entire planet is covered with water? Only if the water is warm enough. So for example, we don't get hurricanes here. If you've ever been to the beach here and you set foot in our water, how does our water feel? Our water is cold. Our water here is very, very cold. Yeah, our water here is very cold. That's why we don't get that's why we don't get hurricanes here. Because the water is too cold to sustain them. So that's good news for us. We don't get hurricanes because our waters are too cold. So we're not dealing with hurricane beta, hurricane gamma, we're not dealing with that because our waters are just too cold. Okay, I have an activity that I want to do today, but before I do it, I also want to spend a few minutes talking about the water cycle. So how many of you have ever heard of the water cycle before? How many of you have ever heard of the water cycle before? A few people. Well, awesome. Good, a few people have heard of it before. Well, let's actually talk about it real quick. So here's how the water, okay, one person says maybe, that's totally fine. One person says maybe. All right, so here's how the water cycle works. So let's start. It all starts on a bright, sunny day over the ocean. All right, nice, bright, sunny day over the ocean. So up here, here's our sun. Draw a little smiley face on it. Draw a little smiley face on it. Our sun heats up the water. Just like it heats up the land, it heats up the water via radiation. That's step one. Sun heats. By the way, I apologize for my horrible penmanship. Sun heats water. Okay, now as the water heats up, what is some of that water going to do? As the water heats up, what is some of that water going to do? It's going to evaporate. Yes. The water is going to evaporate. So, using my pen, H2O, the water evaporates. As the water evaporates, it becomes a part of the air. And so now you have all this warm, moist, rising air. Well, as water rises, it does, as per my corny dance, it expands, it cools, and moisture inside the water condenses. That's the third step. It expands, cools, and condenses. And that condensation forms clouds. Condenses into clouds. So that water condenses into clouds. Well, high above the surface of the Earth, it's a little bit windier than it is down here because there's no friction up there. As a result, these clouds don't stay in one place. Instead, they move. What's happening is as the cloud is moving, it's getting bigger and bigger and bigger. The water droplets inside get bigger and bigger and bigger. And then eventually, it hits land. Eventually, it hits land. Well, as the cloud hits land, and even before the cloud hits land, as it's getting bigger and bigger and bigger, what does the water inside the cloud do? As the droplets are getting bigger and bigger and bigger, what are they doing? So they're condensing into water droplets. They're getting heavier, but what will that eventually cause them to do? They're condensing, they're getting heavier. What will they eventually do? Precipitate. Rain. Precipitation is a fancy word for just water that falls out of the sky. So the water precipitates. Either as rain, as snur, or as other things, but it rains down. Well, our Earth, or at least the land on Earth, is not perfectly flat. Rather, it's very hilly. Well, what happens is all of this water that rains down eventually hits the ground and it runs off back into the ocean. And the cycle begins again. So the sun heats water up, it evaporates, rises in the atmosphere. That water then moves over to land, or rises in the atmosphere, condenses into clouds. Those clouds then move over to land. They rain back down. That water that rains down then runs back off into the ocean, and the cycle begins again. Now, that being said, there are other things that can happen to this water as well. It could rain out before it hits land. That's possible. Or it could fall as snow and then get trapped as ice up here at mountaintops and in really cold areas. Some of the water can actually get absorbed by the ground and become a part of what's called underwater aquifers. I do not know if I spelled that properly, Aquafirs. It's one of the reasons why I majored in math in college. Someday I want to create a spell check for a whiteboard. If I can do that, I might patent it, make $1 million, and still teach because I love teaching. But actually it might be FERS. I think that sounds more right. That's another thing that can happen. Another thing that can happen is it can get absorbed by absorbed by plants. And also plants also exhale it as well. Plants actually breathe out water as well. It can also get drunk by us and then released. There's all kinds of things that can happen to the water. But what I really want you to know is just kind of the TLDR version of the water cycle. The sun hits the water, it gets hot. That causes it to evaporate. It rises in the atmosphere, condenses into clouds, moves over to land, rains out, back down to the ocean. So I would just want you to know that TLDR version. So the TLDR version, ocean evaporates, condenses into clouds, condenses into clouds, clouds, rain over land, and then rain runs off back to ocean. And the process continues again. I actually do have a slide in the next lecture that details this a little bit more, but I just wanted to introduce it now. Okay, so the last thing I want to do for class today is I've had this activity dealing with temperature conversions for a little bit. And so what I actually wanted to do was jump into that activity for the remainder of class today. You can do this on your own, or you can do it in groups if you want to group up with somebody. What I could actually do is have you do this. I can actually open up breakout rooms and have you do it there. But you can also do it by yourself. This is for credit. It is a graded assignment. Let me pop it in chat. And then let me put up the formulas for converting temperatures really quickly. Let me put up a new screen share. So here are the formulas for doing this. So what I'd like you to do is take the remainder of class. When you're done with this, you are done for the day. The only thing is, know that you are actually being graded on if this is correct or not, if what you put down here is correct or not. There are 5 temperatures that I want you to compare, or 5 comparisons I want you to make. I give you a Celsius temperature and a Fahrenheit temperature, and I want you to vote which one is high, which one is hotter, which one is warmer. So take the remainder of class time and do that. There's just 5 of them. I will give you one warning. One of the 5 is a trick question. One of the 5 is a trick question. But that's okay. I promise you, you'll still get it. All right, take the remainder of class time to do that. And then when you're done, you are free to go. And if you need help, I'm still here. I'm still happy to help. And that's it. If anybody wants to pair up, I can, as I said, open up breakout rooms and do that. I can open up, which is hotter? Yep, which one is hotter? That's exactly what I'm asking for. So which one of those 2 is the hotter temperature? Good question. Mm-hmm. Yes, exactly. So somebody just asked, if you have 2 negative temperatures, for example, so let's say you have negative 20 degrees Fahrenheit versus negative 10 degrees Fahrenheit. The -10 would be the warmer of the two. So that's what I'm looking for. The -10 would be the warmer of the two. Hope that makes sense. And if anybody wants to be in a breakout room, just message me and tell me who you want to be in with, and I can pair you up. But you can also do it on your own.
Professor?
Yes. How can I help?
Finished? Can we leave?
Yep. When
Okay,
you are done, you are done for the day. You can leave.
Thank you. Have a good day.
You too.
I have a quick question. So when you say which is bigger, I guess, is that like which one is warmer?
Yes.
Okay.
So I'm asking for which one is warmer. Oh, sure. All right.
Bye, Professor. Thank you.
Bye. Okay. Sign Elizabeth. Okay. Sorry, somebody had a question, so I just went to a breakout room to help them. There any other questions? I'm happy to answer them. Mhm. I just noticed that there are 2 people still in the room. Not a problem. If either one of you has questions, I'm here as long as you need me. Otherwise, I can hang out for a few minutes. Otherwise, have an awesome day. But yeah, I'll hang out for a few minutes if you still have questions. I want to help.